Alright, this section is going to cover the first 8 pages of Part 6 in the course pack, where we begin to discuss stress transformation, failure criteria, and essentially how to deal with these slightly more complicated and realistic cases where we don't just have one direction of stress going on. So way back in Part 2, we looked at these cases of axially loaded glue joints. And if we had one where it was what we called a butt joint, where it's perpendicular to the applied force, this is purely normal stress because it is perpendicular if you look at what's going on in the glue. But when we had this scarf joint, the geometry is different. So you had one component normal, one component along the face, and although it was the same applied force, what was going on within the glue structure, the important thing here is that it is dependent on your reference coordinate system. I mean, obviously, it's the same force, it's the same structure undergoing the same load, but essentially your perspective on it, the coordinate system that you pick, makes a difference. So what we're going to learn is how to deal with moving from one reference coordinate system, like this, and taking a rotation or a transformation to a different coordinate system. And those coordinate transformations are how we are able to find where normal and shear stresses are at their max or their min. And these are the things that we call principal stresses that end up allowing us to analyze structures that have both normal and shear stresses going on. So with that introduction, we'll start looking at the actual geometry of the case. So if we talk about any particular structure out in space, a general stress state, as we looked at the beginning of the combined loading, there are basically 6 reactions or 6 linear, 6 forces, 3 linear and 3 torsional, 3 moment reactions that can happen, and those translate into this 3-dimensional general stress state. So we can have normal stresses on each of the faces. So we have a sigma x, a sigma y, and a sigma z. Now, we also have 3 shear stresses. And we have one in our terminology. This one is our tau xy, meaning it is acting on the x face in the y direction. And using that same convention, this guy is tau yx. It is on the plus y face, pointing in the x direction. Okay, we'll go for blue. We have a pair along this face, where this guy is our z face in the y direction, and this one is on the y face pointing in the z direction. And our last triple, we'll put in red, would be this way, where we have on the X face in the Z direction and on the Z face in the X direction. And really that's just half of them, because there are also analogous stresses on each of the 3 hidden faces as well. So, how do we keep this from being an absolutely untenable situation? Well, we will learn how to deal with it in matrix form for one case, but there's also some simplifications that we can do. But first, I guess this collection of values, stress, is what we call a second order tensor. We have 3 squared values, and you can use these transformation matrices to go from one coordinate system to another, which is what we're going to work through the detail of. As a side note, forces and displacement are what you call a first order tensor, 3 to the 1 values, but they also you can do these coordinate transformations on them as well. If we assemble our stresses from our drawing above into matrix form, we have our normal stresses end up going along the diagonal, and we have a jumping matrix. We have a diagonal matrix where these elements are across that diagonal of normal stresses from each other. And we've got our Z's, and then we have our XZ and CX out here at the 1, 3 and the 3, 1. Now, because this ZX and XZ, in order to maintain equilibrium, there are a few of these that we can say we know that the magnitude has to be equal. So we can say that XZ is equal to ZX. We can say that YZ is equal to ZY. And we can say that XY is equal to YX. So that simplifies things a bit into a truly symmetric matrix. Now, in the cases that we are dealing with in this class, with the exception of the thick-walled pressure vessel case, which is in Part 5, everything that we've dealt with has had a single normal stress and a shear stress, or 2 normal stresses in the same plane. So when you have that characteristic, we call it a plane stress case, and we can say that the following: we know that sigma z is 0, we know that tau xz is 0, and we know that tau yz is 0. So if we look back up at our symmetric stress matrix on the bottom of the previous page, we're saying that this is 0, that this, and therefore that, is 0, and that these terms are 0. So we end up with a plane stress case where we have sigma x, we have sigma y, and on the diagonal we have our shear stress tau xy. This is the state of plane stress, and this is what we will be dealing with. We have up to 3 values, sigma x, sigma y, and a single shear stress. So, how do we now deal with these coordinate transformations? If we have an original xy coordinate system and we want to move the quantities that we're dealing with into a new coordinate system that we're going to call x prime, y prime. So this is the scenario that we're talking about, moving the coordinate system through a rotation angle theta. And we come back to our block of material that is in plane stress. So we have a single shear stress, is our tau xy, also on the corresponding bottom and left face. We have a normal stress in the x direction, and we have a normal stress sigma y in the y direction. The plane stress says that the rest of them are 0. Now we're going to take a section, we're going to take a cut in our new x prime direction, and that's indicated by this plane slicing through the cube, and that's at this direction, or at this angle, theta, through our cube. So our tau x prime y prime is going to be defined as the shear stress on the x prime face in the y prime direction, and likewise the sigma x prime is the normal stress in our new x prime direction. So what does that look like? That looks like a sigma x prime here. We have our old sigma x here. We have our old sigma y here. We have our old shear stresses along the back face. So this is our tau xy, tau xy, and we have our new shear along the cut face, tau x prime, y prime. So this triangular block, or this wedge structure, is our new structure that we're going to write our equilibrium problem, and that will give us our stress transformation. So this drawing up here is stresses. We can't do equilibrium on stresses. We have to do equilibrium on forces. So generally, stress is force over area. So if we want forces, we need to multiply stresses times our areas. So this breaks down our wedge in terms of the geometry of it so that we can get our areas. This is our width W. We know that this angle is theta, and we know that along the face we're going to call this 1 unit. That's unit length. So we know that the area of this face is our width W times our 1 unit. We know that this side opposite is sine theta. We know that this vertical is our cosine theta. So the area of the back face is the width times cosine theta, which is this. This is our sine theta. So we know the area of the floor, so to speak, is our width times sine theta. And those are our three faces of interest. How does that translate into forces? For our shear stresses, the shear stress along this direction, we need to multiply that times the area of that face, which is W. So we have tau x prime, y prime times W. For the force acting on the bottom face, for that resultant, we have tau xy times the area of the bottom, or the floor, which is W sine theta. And for our downward force acting on the back surface, we have tau xy times the area of the back, which is W cos theta. Okay, that takes care of the forces due to the shear stresses. And now for the forces due to the normal stresses. Forces due to normal stresses in purple. This is our sigma x prime times the area of the face W. We have a downward sigma y times the area of the bottom face, W sine theta. And we have outward a sigma x times W cosine theta. So those are our forces. We have mixed coordinate systems. We have the ones on the cut face are in our x prime, and the ones on the bottom and the back face are in our regular xy. So what we need to do is move everything into the x prime, y prime coordinate system. And we'll do that in turn on the normal stresses. We know that the one on this face, this force, is already in our x prime direction, and its magnitude is sigma x prime W. And in the x direction, in a dotted line, we have sigma x W cosine theta, and we want to resolve that into components in the x prime and y prime directions. Same with this, which has a magnitude of sigma y W sine theta. We need to resolve it into components in the x prime and y prime directions. So, starting with this one, we know that it is the resultant, sigma x W cosine theta, times, and this is our rotation angle here, and that's our rotation angle here, so we need to multiply this one times sine theta to get this component, and we take the magnitude in the x direction times cosine theta for this component. Similarly here, sigma y W sine theta times cosine, and sigma y W sine theta times sine theta. That gives us all of the components of the normal stresses in our new coordinate system. Looking at the shear stresses along this face, this one is already in the new coordinate system, and we have one here whose original magnitude is tau xy w sine theta, and we need components in the x prime and y prime direction. Same here. This original is tau xy w cos theta, and we need components in the x prime and y prime direction. Starting here, tau xy w sine theta times sine theta, and tau xy w sine theta times cos theta, tau xy w cos theta times sine theta for this side, and tau xy w sine theta times sine theta for this component. All of that simply gets us to the point of being able to do the statics problem. So summing the forces in our new x prime direction, starting with our components that are in, or that are from our normal stresses. We have sigma x prime times w in the positive x prime direction. We have sigma x w cosine squared theta and a minus sigma y w sine squared theta. That's looking back at this drawing and looking at what we've got in the x prime direction. We have this one, we have a cosine squared term, and we have a sine squared term. Both of those are in the minus direction. Alright, so now looking at the shear stress contributions, we have a cosine sine in the minus, and we have another cosine sine in the minus x prime direction. So we have minus tau xy w cosine theta sine theta, and a minus tau xy w sine theta cosine theta. And all of that has to equal 0. So the first thing that we can see about this kind of cumbersome equation is that w will drop out, and now we need to solve for our sigma x prime. So isolate for sigma x prime, and we get sigma x cosine theta sigma y sine squared theta, and 2 tau xy sine theta cosine theta. Okay. Now, looking at the same process for the y prime direction, what do we have left here? We have a cross product term times the normal stress in the x direction. We have a cross product term multiplied by the normal stress in the y direction. And that looks like plus sigma x w cos theta sine theta, and the minus sigma y w sine theta cos theta. Now looking at the balance of the terms from the shear, we have plus this guy, and minus this guy. So pulling that into the equation, we have a plus, the one that's already in the x prime, y prime direction, minus tau xy w cosine squared theta plus tau xy w sine squared theta equals 0. And now instead we solve for our shear stress in our new coordinate. We again see that our w's fall out of the equation, and we see that our new shear stress in our x prime, y prime direction is minus sigma x cross term plus sigma y cosine theta sine theta as a cross term plus tau xy cosine squared theta plus tau xy, nope, sorry, that's a minus, minus tau xy sine squared theta. So, if we then wanted to find our sigma y prime, we could take a new section cut and do the process that we just did before, but we can also recognize and use our sigma x prime equation if we are clever and see that our y prime direction is really separated simply by 90 degrees. So we have this situation where we have our x and our y coordinate system, and we look at our new coordinate system. If this is theta, then we know that this is theta plus 90 degrees, and we know that cosine of theta plus 90 degrees is minus sine. We know that sine of theta plus 90 degrees is cosine, and so we can simply kind of jump to the answer that our sigma y prime is sigma in the x direction times sine squared, and cosine squared times the normal stress in the original y minus the shear stress times a cross term. Now all of these, this, and this one up here, our sigma x prime, our tau x prime y prime, and our sigma y prime can be gathered into a transformation matrix. So if we, for example, look at our sigma y prime, we have sine squared times our sigma x term. We have cosine squared times our sigma y term, and we've lost a 2. We have minus 2 cosine squared sine squared times our shear stress term. This is our transformation matrix. So this process gives us a transformation matrix that allows us to go from an arbitrary stress state, sigma xy and tau, sigma x, sigma y, and tau xy, to a transformed coordinate system that is rotated by an angle theta into this new coordinate system. So going through an example, if we have a stress state where our x direction stress is 8,000 psi in tension, we have 3,000 psi compression in the y direction, and typo in the course pack, we have a tau xy shear stress of 6,000 psi. We assign those in the vector for the original untransformed stresses, and we want to rotate this into a new set of axes at 30 degrees from the original, and we simply do the matrix math. So sigma xy equals cosine squared of 30 times 8,000, and sine squared of 30 times minus 3,000, and 2 times cos 30 sine 30 times 6,000, and the sum of those is 10,446 minus 5446 and minus 1763 is our set of transformed stresses. If we look at this, the original is our sigma x of 8,000 psi tension, sigma y 3,000 psi compression, and a shear stress of 6,000 psi. And I know that that shear stress is positive because you look at the positive x face. It is in the positive y direction. I have to remember our sign conventions for that. Now, we rotate this by 30 degrees. So we have our new rotated element of material. Our sigma x prime, our new x direction, is a much larger 10,446 psi. We now have a slightly larger compression in our sigma y prime direction is 5446. And now here's the difference. We have a negative shear stress. So if we look at the plus x prime direction, we need to draw this shear in the minus y prime direction. So tau x prime y prime is minus 1763. So note that there is a sign change there. So these new transformed coordinates, or these new transformed stresses, so over here is our transformed state. So our sigma x prime is 10,000 and something. That's larger than our original sigma x and sigma y that were 6,000 and 10,000 each. So if we've rotated by an arbitrary 30 degrees and gotten this, there is some value of theta where we're going to end up with a maximum sigma x. And it's that value that we call the maximum principal stress, and it's that value that we need to figure out the overall effect of a given stress state so that we can do failure analysis. So this next page, this plot, is looking at basically the transformed values of sigma x prime in the blue, sigma y prime in the red dot, and our shear in the green dot, and what happens at these various angles. At theta equals 0, we have our original stress state of sigma x 8,000, sigma y positive 6,000, and a minus a positive 6,000 shear and a minus 3,000 sigma y. That's our original stress state. We then rotated by 30 degrees. And we got a sigma x that is slightly over 10,000. We got about a minus 5,000 sigma y, and about a minus 2,000, or minus 1763 to be exact, on the shear stress. You can see as you change that theta angle of direction or angle of rotation, you have sinusoidal variation of each of these transformed stresses. The very important thing that you see is that at a rotation angle of approximately 25 degrees, you have the largest value of sigma x prime, and that corresponds with the smallest value of sigma y prime. Then, if you go, so that's at this location, if you go 90 degrees from that to about 115, at theta is approximately 115 degrees of rotation, or 25 plus 90, then the opposite is true. You have sigma y prime is maximized, and sigma x prime is at the smallest value. Okay? Another very important thing to note, if sigma x prime or sigma y prime are at a max or a min, what's the value of the shear stress there? The corresponding value of the shear stress at these normal stress max and min is 0. Also, the shear stress is at a maximum or minimum at 45-degree rotations from the maximum normal stresses. And where you have maximum or minimum shear, that corresponds, so if we look here, where the shear stress is at a minimum, that corresponds to the x and y principal stresses being equal. And also here we have shear stress is a maximum, and that corresponds to the normal stress in the x and normal stress in the y being equal. So how can we find these very important values? If we start with the fact that we have just derived the fact that sigma x prime is equal to this expression, our cosine squared of theta, times the untransformed normal stress in x, plus the sine squared of theta, times the untransformed sigma y, plus 2 times cosine times sine times the untransformed normal stress xy. If we want to maximize that expression, we need to take the derivative with respect to 0, set it equal to, take the derivative with respect to theta, set it equal to 0, and we end up, fast forwarding through sort of the gory detail, we have one value is equal to the inverse tangent, 1/2 the inverse tangent of the shear stress over half of the difference between the normal stress in the x and normal stress in the y. So that denominator. And then the other angle is 90 degrees separated from that. If we then take those angles and put them back into the expression for the transformed normal stress in the x direction, we get that the normal stresses at this angle A and angle B are the mean of the untransformed normal stresses plus or minus the square root of this difference squared and the shear stress squared. A note about nomenclature: some places will note these as sigma 1 and sigma 2. We're following the FE handbook, which notes these as principal stresses sigma A and sigma B. And applying these equations to the example that we started with, where we had sigma x of 8,000, normal stress in the y, a compressive 3,000, and our shear stress of positive 6,000, sigma A and B are 8,000 plus or minus 3,000, that's the mean. Then plus or minus this quantity where we subtract and take half that quantity squared and the shear stress of 6,000 squared. This ends up with 2,500 as the mean value, plus or minus 8139. So we end up with two values, one of which is 10,639 and the other is minus 5639 psi. These are what we call the principal stresses. Where do these occur, or at what angle in the rotation or transformation matrix? These occur at theta A is 1/2 times the inverse tangent of the shear over this difference and that ends up being 23.75 degrees, and the other one is 23.75 plus 90, or 113.75 degrees. And if we scroll back to our somewhat messy plot, we see that at 23 degrees, we do, in fact, have this maximum. That value is 10,639. This value is minus 5639. This occurs at 23 3/4 degrees. 90 degrees separated from that, you have the other principal stresses at 100 and almost 14 degrees. The next step is to learn how to do this process graphically, and that is Moore's circle.